So welcome to Computability and Complexity. In this MOOC we'll have a look at problems like, for example, this one. You have a program written, for example, in C or in Java containing loops, and we would like to know whether the loop terminates or not. It would be great. We would also like to know whether some line of code is actually reachable, whether it can be reached during the program flow or not. These are typical programs that you might face when developing computer programs. And in this MOOC we'll see that unfortunately, in general, all these problems are undecidable. So there is no hope of ever getting a tool that will help us in each and every situation with these problems to actually check whether our program will terminate or not. That's the first part of the course. The second part of the course will focus on complexity, and in complexity there are a lot of problems that we can actually solve, but we have no idea whether we can solve it efficiently. Typical problems in this case is route planning, for example. That's a quite typical problem. However, it's up to now unknown whether there exist efficient algorithms for this. We'll especially consider time and space as typical resources we'd like to know something about. In this course we do it formally, so we need to have a formal model of our computer. So instead of using a general purpose computer, we'll stick to a more formal model, that's the so-called Turing machine, which can actually do everything our normal computer can do, and vice versa. Our normal computer is of course able to simulate a Turing machine. Turing machines are just automata that have an infinite tape. It's a very old model. It goes back to Turing apparently, and he invented it and giving it an infinite tape that can be written on, read on. So the contents of the course is we start with the definition of the Turing machine, then go to undecidability in general and look at the halting problem and derive other problems that are undecidable. We'll have a look at reduction to make all these proofs. We then generalize this to Rice's theorem, which more or less says that every interesting property about programs and Turing machines is undecidable. And after having dealt with all the bad news, we go to the complexity part, having a look at the classes P and NP, which describe time complexity classes, and then we move on to space complexity classes like P space, NP space, L and NL.